Yes.
And then I would like to wish good afternoon to everybody. And I am happy that I can share our results with you on our recent researches on the rapid determination of actinides in water samples using TIVA and Tk221 resins. And this work has been performed in cooperation with Triscam. Thank you for that, and especially with Stefan Happer. So what I'm going to speak about is the properties, just briefly, of TIVA and Tk221. Then we did model experiments to optimize this procedure for actinide separation on TIVA and on Tk221. And finally, we did some experiments for the determination of actinides in tap water and seawater samples. So the goal of our work was to develop a combined procedure for the selective separation of plutonium, americium, curium, uranium, neptunium, thorium using chromatographic resins. So the procedure should be adequate for water samples, for alpha spectrometry. It should be rapid and robust to analyze actinides of elevated activities, not just normal activities. And we would like to apply this procedure for analyzing water samples like processed water or contaminated water, drinking seawater in emergency situation. So for this purpose, we needed resins of high distribution ratio and also of high selectivities for actinides. So we should discuss now a little bit the properties of actinides on certain specific resins. In the past, we tried to use always a single resin for the separation of all actinides. This is what we call single column option. And this is usually a cheap solution, but the separation is usually sensitive to the conditions. So sometimes we had to make temperature control so that we can stabilize the whole elution sequence. The other option is a so-called multi-column option when we use several resins which are specific for certain actinides. So it is a more expensive option, but in this case, the separation can be more robust. So this time we made this multi-column option. So I would like to speak a little bit about 3 common resins. And here you can see the capacity factors as a function of the nitric acid concentration. So TIVA, as you know, is a quaternary amine, and how its name says, it's for tetravalent actinides, so it can retain plutonium, neptunium, thorium as tetravalent species. The true resin is a carbamoyl methylphosphine oxide derivative, and it can retain tetravalent actinides as well as hexavalent, and to a certain extent also trivalent actinides. And then we use DGA resin, the normal DGA, a diglycolamine, and this resin can retain all actinides to, let's say, the hexavalent uranium to somewhat lesser extent. So if we load a mixture of actinides from 3 molar nitric acid on TIVA resin, then it will retain plutonium, neptunium, and thorium in the tetravalent form. If you load the same solution onto a true resin, then beside plutonium, neptunium, and thorium, you can also retain well uranium, but not very well americium. And under the same conditions, americium will be retained on the DGA resin, and you will have losses of uranium. So if we retained plutonium, neptunium on the TIVA from 3 molar nitric, then we have a chance to separate them from hydrochloric solution. So here you see the capacity factor as a function of hydrochloric concentration, and if you use 9 molar hydrochloric, then thorium can be easily eluted from the column. And with a dilute acid, you can elute plutonium and neptunium as well. If you use the true resin and you have already retained plutonium, neptunium, thorium by the TIVA resin, so you have americium and uranium and load it from 3 molar on the true resin, it will retain uranium well and americium partially. And from this resin, you can strip americium, the rest of americium with a dilute hydrochloric and 0.25 molar hydrochloric, while uranium is still partially on the column, and you can elute it with ammonium bioxalate. And now if you look at the DGA resin, it can retain americium from 3 molar nitric, and it can be easily stripped with dilute hydrochloric, like 0.25 molar hydrochloric. So now we came to the Tk221 resin, which is a relatively new resin produced by Triskam, and it's a combination of true and DGA resins. So it was designed for the separation of lanthanides, and it seems to be adequate for the separation of actinides as well. Out of the natural matrix elements, only calcium is slightly retained on the resin from nitric solution, but it can retain many trivalent and tetravalent elements like iron and zirconium from the same medium. So we made up a concept for the separation. You can see this basic concept here, where actinides are pre-concentrated from the water sample on calcium phosphate as a co-precipitation. Then oxidation state adjustment occurs, so to get tetravalent actinides from plutonium and neptunium, and we pass the the sample from 3 molar nitric acid through a stacked TIVA Tk resin cartridge. Then we separate the TIVA and the Tk cartridges, and we elute the separated cartridges independently. So from the TIVA cartridge, we can strip thorium with 9 molar hydrochloric, and we can strip plutonium and neptunium together with dilute hydrochloric. From the Tk resin, we planned to elute americium with dilute hydrochloric, and finally uranium with the ammonium bioxalate. We prepare usually alpha sources from the strip solutions, and you can see here that plutonium and neptunium appear in the same fraction. So we made a modification to this separation scheme to separate plutonium and neptunium as well. So from the TIVA column, we try to elute plutonium also from 9 molar hydrochloric with a strong reducing agent titanium that turned it to plutonium-3. And after plutonium strip, we try to elute neptunium with dilute hydrochloric. So in this case, we could get 5 alpha sources. And we tested both procedures. So the first part of the testing contained the optimization of the chromatographic separation. And first, we optimized the americium-uranium separation on the Tk resin. For that, we made a model solution, modeling water samples. So we added calcium and iron to the load solution, adjusted the oxidation state as normal, and added to each sample a single radionuclide tracer of relatively high activity, and we measured all the fractions using liquid scintillation. And by this technique, we got the chromatogram of the separation. And from the first one, you can see that we got immediately quite a good separation between americium and uranium. And then we added calcium to the load solution, and we were surprised to see that americium could not be eluted, and the separation was not so good as before. So what we did then, we increased the volume of the eluent for americium. This you can see in the next figure. And with increased eluent volume, we could separate americium from plutonium quite well, even in the presence of calcium. So it is an interesting question what happens here, and we don't know the exact mechanism why the presence of calcium will change the elution behavior of americium. But we had some similar experience with the DGA resin, that its mechanism is influenced by the presence of calcium. So now we did another model experiment with all the actinides, again with individual spikes, to see whether there is some contamination in the TIVA-TK complex system. And we found that americium-uranium separation is still okay. There is no contamination. You could see some uranium losses in the rings. And we also did model experiments to test the behavior of all these actinides on the TIVA columns for the original scheme and also for the modified scheme where we separate plutonium from neptunium. And you can see that thorium and plutonium were perfectly separated in both cases. Unfortunately, we had no neptunium tracer to test directly the behavior of neptunium, but in the neptunium fraction, there was no plutonium. And here you can also see some uranium leaking from the system. So here are the results of the model experiments, results of the optimization. You can see the recovery of each actinide, and you can see that the recoveries for each actinide in the strip solution is close to 100%. And there is only one possible contaminant in the fractions, and this is uranium, which is leaking a little bit, but the contamination is usually less than 1%. So we were satisfied with this test. So we went to the real samples, real water samples, and in this case we used a normal tap water, and we used the seawater. Each of them were of 800 milliliter volume, and we spiked each of them with all 5 actinide tracers. The actinides were co-precipitated with the calcium phosphate. The chromatographic separation was performed as designed. In the first set of experiments without neptunium separation, and the second set with neptunium separation. And alpha sources were prepared by microprecipitation. And here you can see the results, the chemical recoveries for the tap water samples and for the sea water samples. So what you can see that the chemical recoveries for all actinides, I would say, are acceptable high, which means more than 60%, sometimes close to 100%. You can also see that the chemical recoveries in the tap water are always a little bit higher than in the seawater, showing the matrix effect. There was only one detectable contamination in the alpha spectrometry, and this was a small amount of plutonium appearing in the neptunium fraction, but it was also less than 1%. And I have only one more remark about preparing the plutonium sources from the 9 molar hydrochloric solution here and here. So in this case, we found out that you cannot prepare a plutonium source with good recovery directly from the 9 molar hydrochloric. It should make a strong complex. So you have to evaporate it and dilute it. And after this treatment, you will get a good recovery for plutonium. So as a conclusion, I can say that this new procedure has been elaborated for the separation of uranium, plutonium, americium, curium, and neptunium in water samples. Actinides are pre-concentrated with calcium phosphate. Chromatographic separation is performed on Tk221 resin cartridges, and alpha spectrometry is used directly. For all actinides, the chemical recoveries are acceptable high. The decontamination factors are also equal or better than 100%, than 100, sorry. And the resolution of the alpha sources are good. Sensitivities of the method are acceptable high, so the detection limit is lower or equal to 0.1 becquerel per kilogram. And I would say that this procedure seems to be robust, and the whole analysis can be done in 1 day. And thank you for your attention.
Yeah, thank you very much, Nóra.
Thank you.
Thank you. Very nice presentation. And indeed, I think the Tk221 has this, quite I think some potential for it. And I think at some point we will look into samples with even more matrix, see what's happening in more iron-rich samples. So I think the fact that americium and uranium are both well retained might be quite interesting even for higher matrix samples. So I'll get back to you for some more. Okay, thank you very much again.
We look forward to it.
Okay, there's a question actually. So from NASA, he's wondering if water samples that contain tritium and C14, if they will be co-absorbed by the TIVA resin. That's a tricky one. I think on. So from experience with the tritium columns, I would say the tritium, as long as it's HDO, there's really no risk. The C14, that will probably to a certain extent depend on what exactly, how the C14 is present. I mean, carbonates are typically destroyed from the acid at some point, so they will be eluted. So I wouldn't expect too much retention, but for the C14, it might depend on how exactly it's going to be present, I think. Okay, there's another question. Okay, there's plenty of questions. From Juana, hi. Which is the reason to add aluminum nitrate to the sample load?
Aluminium
Yeah.
is a salting out agent in this case. So it increases the nitrate concentration without increasing the acidity. I think that's the role. So it would work without aluminium also.
And I think in that type of water samples, the amount of phosphate that you add is fairly reasonable. But yeah, the aluminum is also complexing the phosphate that's present, and that's helping with the retention of tetravalence. Otherwise, phosphate tends to interfere a bit with the retention of tetravalence.
And actually, this aluminium concentration is high in the load.
It is very high, and it's the more phosphate, the more aluminium. Aluminium is always good. It's salting out. It's helping against phosphate. As long as you have a pure aluminium that has been purified, that's a pretty good thing. Okay, one more question from Andreas. Oh, hi, Andreas. Yeah, the old question of internal standard for the Neptunium. So yeah, that's a very tricky one. So Neptunium 239, yes, possibility, but it's not an alpha emitter. So yeah, that's a tricky question. If you have any,
we have the option to prepare or to get irradiated uranium, and from this irradiated uranium we can separate the Neptunium 239 to use it as an internal standard. But actually the reactor is not running continuously. So, for example, it was not running in the last half year. So that therefore, but we could also use this tracer just to make the original test with the individual actinide. So if some more, I would say if the reactor is available, then we could add some more tests. But to use it as a tracer regularly, I don't have big hopes.
yeah, and you need a second measurement. That's always a very tricky one in terms of uncertainties and everything. So Neptunium is quite difficult. So I think quite a lot of publications tend to have plutonium and Neptunium together in the fractions and try to trace with the plutonium. So the easy way out in a way, but it's its own challenges. Okay, yeah, from the unwritten truth future. Okay, are there any more questions? If not, again, thank you very much.